So let's look at this one. See, I'm just choosing randomly some of those which I'm finding a bit interesting. You are given this relationship between it's an equation satisfied by a function. So it's a implicit equation satisfied by a function. People usually don't even call that it's an implicit equation. They just say an equation satisfied by a function. Regarding f as a true function, it may satisfy a certain equation. If you go looking for the solutions of this equation, then you may realize that you have more than one function which satisfies this equation. But that's besides the point. There is a function, one or more than one function, which satisfy this equation. You're given this. And you have to find, excuse me. You have to find f derivative at x is equal to 1, given that the value of f at 1 is 2. So all you need to do is start differentiating. The equation, you get f derivative of x plus, now the product rule, the derivative of this term and the second term as it is. And then this as it is, and the derivative of the second, which by chain rule, you just take the derivative of this guy, bring down a power, and then derivative of what is inside. And on the right hand side, you have a 0. Now you have got an equation now which describes for you some relation between f derivative and f of x, which is true at any point. So you can put in in general, if you try to solve for f derivative, you can take the other things, separate out and put the other things on the other hand, on the other side. However, unless you know f of x, you won't know what is f derivative of x. But here you are given that this condition. So if I just put in x is equal to 1 in equation 1, equation A, I get f derivative of 1 plus 2 times 1, and f of 1 was given to be 2. 2 cube plus 1 square, 3 times 2 square, f derivative of 1 is 0. So you get 1 plus 12 plus 2 to the, this is 16. So that's the answer. And all you did is take a implicit derivative. Let's take a similar one. So here you are given this. And you have to find at 0 the derivative of g at 0. This is not plus x squared, this is the equation. So again, just compute the derivative. You get g derivative of x plus x as it is, and the derivative of sine, which is cosine, and then the derivative of what is inside. And here just 2x. Now, if I put x is equal to 0, I get g derivative at 0 plus sine g of 0 plus 0, this whole term becomes 0, and this becomes 0. So that means the derivative of g at 0 is the sine of g of 0. Whatever value you get here, that will be your answer. Let's take this one. You're given this. And you want to find dy by dx. So I'll call it again as y dash. Makes things easier to read when you are doing this kind of implicit differentiation. So you don't have to, the point is you don't have to solve for y. Just take derivative of this equation. Differentiate the above equation. And I don't really recall what's the derivative of secant. So I'm just gonna write it like this. So y is x cosine x times sine y over cosine y. Well, let's just write it as, keep it as tangent y because the derivative of that is easy enough. Now differentiate. So you get y derivative is equal to, we have to do the Leibniz rule. So 1 cosine x tangent y as it is plus x derivative of this whole thing. But as you can see that when I'll do the derivative of this whole thing, I'll be doing Leibniz rule on these two one by one. So in essence, what the Leibniz rule becomes on a product of more than 2 is that you leave one alone, leave 2 alone, and differentiate the other one, and just keep adding. So I get plus x, the derivative of cosine is sine x, tangent y, plus, well, minus sine x, plus x cosine x, the derivative of tangent y. You're differentiating with respect to x, tangent y. Now, all you have to do is try to simplify it. Minus x sine x tangent y and the derivative of tangent y, as we recall, is secant square. So secant square y and times, now you do the derivative of what is inside. So what's inside is y. So y dash. So you have cosine x minus x sine x is tangent y. And I can take this to the other side. X cosine x over cosine square y. That's what I have got. Now, in general, you are left with something complicated. And what you need to do is try to see if you can do something, some relation from here to try to simplify it. Well, what I can do is I can put in this value. Tangent y is y over x cosine x. And then if I look over here, I have y. So I get y dash is now the issue is that we have to find dy by dx. If you leave like this, this is the answer. But what is this as a function of x? Doing that is usually not that easy unless you are putting a value, or you can see you can use it in some intelligent way. to find, so like for example, from here, I see y over tangent y. Tangent y was y over x cosine x. Y is x cosine x. So if I divide by cosine square, uh, 1 minus sine square y minus x sine square. So not that easy to find, so let's leave it over here for now. Now let's look at this one. So suppose we are given this. Y sine 2x, x cosine 2y as equation of a curve. And we have to find equation of the tangent at this point, pi by 2, pi by 4. This is the x value, this is the y value. So cosine well, first let's check, does this point lie on the curve? So y is pi by 4 times sine of 2 pi over 2 pi by 2 cosine of 2 pi over 4. So sine of pi is 0. And over here I have cosine of pi by 2, which is 0. So this equation is satisfied. So this does lie on the curve, because this equation is satisfied. So at this point, we have to find the tangent. So all you need to do is differentiate. So what do I get? I get y dash sine 2x then y as it is, cosine of 2x times the derivative of what's inside, which is 2, then cosine of 2y plus x as it is minus sine of 2y times 2 times the derivative of what is inside, which is 2y, so that derivative is 2y dash. Now, what I'm after is all I need is y dash at the value of x pi by 2. And I need it when x is pi by 2 and y is pi by 4. This point. So I can put this here, and then I don't need to solve for y dash as of in a functional form. I'm just solving for an algebraic equation, so much easier to do. So I get y dash of pi by 2 is sine of 2 pi by 2 and plus, wait, I'm sorry about this. I think he's using this symbol. Let me see. No. Because if I put pi by 4, pi by 4 here, so I get sine of pi by 2, which is 1, cosine of just minus 1. This is fine. Yeah, okay. Sine 2 pi by 2 and y is pi by 4, cosine of 2 pi by 2 times 2, cosine of 2 pi by 4 minus 2 pi by 2, then sine of 2 pi by 4 times y derivative of pi by 2. This is what we need. So over here, I have a sine of pi. So this goes to 0. So this one gives me pi by 2 and a cosine of pi, which is a minus 1. And over here, I have a cosine of pi by 2, which is 0. And over here, I get minus pi and sine of pi by 2, which is 1, times y dash of pi by 2. So that means y dash of pi by 2 is simply half. And this is simply the slope of tangent. Line at this my required point. So the point is given. And slope is known. So you can write the equation of the tangent. And let's consider another example of this kind. So this, let's call it problem. I don't know, it's 5th for today. This is an equation of an ellipse. And we are finding tangent at 1, 1. So you get, just differentiate, you get 2x plus y plus xy dash plus 2y y dash is 0. And now you just have to put in, for y, you have to put 1, and for x, you have to put 1. At 1, 1, I get 2 times 1 plus 1 plus 1. This is not 1. This is y derivative at point 1. So you get y derivative of 1 times 3 is equal to minus 3. So y derivative of 1 is minus 1. It's a line like this. Is this worth doing? Let me see. Problem. Zero minus 2. So this is called, well, there are many interesting curves which are given in the book. I'm picking this one. This is called Devil's curve, because if you trace the points which are satisfied, they look like this. And you need to find the tangent here. So it should be something giving you a slope of 0. That's your answer should be. And this point on this curve at x is equal to 0, there are many different solutions you have. So if I put, I'm looking at x is equal to 0. So in this curve, when x is 0, this is satisfied. So that tells you that either y is 0 or y square is 4, that is y is plus or minus 2. And you can see that there's this point, and this point corresponding to x is equal to 0. They're all satisfied by this curve. So they're all over here. We are interested in this point. So this, we are picking 0, minus 2. What is the curve over here? What is the tangent over here? Now, just a remark, you can see that I had a y square. So the solution that y is equal to 0 is kind of double, because y becomes 0 2 times. That corresponds to these two different branches. but we haven't learned these techniques yet. That how do I know that it will correspond to two different branches? But in any case, I'm interested in this point. Change it at here. So what do? I just take differentiate. So when I differentiate, I get 2y, y dash, this guy as it is, plus this guy as it is, and the derivative of what's inside. So 2y, y dash, 4 is a constant, gives you 0. And then on this side, I get 2x, x squared minus 5, plus x squared, 2x. That's it. Now I put these numbers here. So I get 2 times minus 2 y derivative and minus 2 square minus 4 plus minus 2 square times 2 times minus 2 times y derivative, which is at this particular point, not any other. And over here, they all become, I have a 0 here and a 0 here. So this side is 0. And over here, I have this guy is 4 minus 4. So this term goes to 0. While this term gives me minus 16, y derivative of 0 is 0. So the only solution to this is that y derivative of 0 is 0. So slope is horizontal, or tangent is horizontal. As it was obvious from the graph. Let's consider this. So given xy plus ey is equal to e, where this is the Euler's number, find the value of y double dash at a point, at the point where x is 0. So this is a relation between x and y, and it will correspond to some curve. We don't know what that curve is, but we need to find the value of y double dash at the point when x is 0. So when x is 0, the above relation gives us, what I'm doing is just putting x is equal to 0 to see that what is the value of y at when x is 0. The above relation gives us 0 plus ey is equal to e. So ey is equal to e. So how is it possible? It's only possible when This implies that y is 1 when x is 0. So I take this, I differentiate. I get y plus xy dash plus ey y dash. That's the chain rule. And on the right hand side, this is a constant. I get a 0. So I have this relation, but I haven't gotten a y double dash. I need y double dash, which is by definition the second derivative, which is equal to derivative of y dash. So I differentiate again, because when I will differentiate, I will be differentiating the terms involving y dash, and those will give me create for me a y double dash. So when I differentiate with respect to x, again I get y dash plus the derivative of x, y, that gives me y dash, plus x and the derivative of y dash, which is y double dash. Let me write it explicitly first. So then I come to this term. I get the derivative of first term, which is ey y dash, and y dash as it is, plus ey, and then derivative of the second term. Then right hand side 0 differentiated still gives you 0. So this gives me 2y dash plus x, derivative of y dash is y double dash, plus ey y dash square plus ey y double dash is 0. Now I want to put the values. X is equal to 0 and y is equal to 1, because that's where we want to find the value of y double dash. But I have a problem. When I try to put this in, what will I put for? What is y dash at x is equal to 0 and y is equal to 1? To do that, I'll have to go back to this equation and compute it from here. I need the value of y dash in this equation at x is equal to 0 and y is equal to 1. But that can be computed from here by putting x is equal to 0 and y is equal to 1 in this equation. So let's call this A. Put in equation A. That gives me 1 plus 0 plus e y dash of 0 of my specific point is 0. So that gives me y dash of 0 is minus 1 over e. So I have to take this plus this plus this. This is the point where I am at, and let's call it B. put in B. So the first one gives me 2 to the minus 1 over E. The second term just becomes 0. Good thing, we just get rid of it. Then I have a E. Then Y derivative, as I know, is minus 1 over E square plus E and Y double derivative, the value which we are after. So this gives me minus 2 over E plus I have a 1 over E square E, so this gives me 1 over E. So I get E is equal to minus 1 over E. And that implies the double derivative at this point is minus 1 over E square. Now let's look at this problem. So you are given this curve. This is called a bouncing wagon curve. Because of its shape, but that doesn't concern us. The curve is described by this relation. We have to find at how many points it has a horizontal tangent and what are the x coordinates where tangent is horizontal. Not sure if it can be done from here, but let's try. So horizontal tangent means that y derivative of this special point, let's call it x tilde is 0. Because this implies that the slope is 0. So just compute from here, differentiating, we get 6y square plus 2y, well, 6y square, y derivative, plus 2y, y derivative, minus 5y, 4, y derivative is 4 x cube minus 6x square minus 2x. So that means the derivative is given by this relation. And we want this to be 0. So for this to be 0, you need 4x cubed minus 6x squared minus 2x to be 0, and 6y squared plus 2y minus 5y4 not 0 at those values of x. So from the looks of it, I can see that I have x times 2x squared minus 3x minus 1 is 0. So it's a cubic equation. You have 3 roots, which we can try to find out. So from here, I got this. So this implies x is 0, or 2x squared minus 3x minus 1 is 0. I just want to make sure I didn't do any mistake. 4x cubed minus 6x squared. Yeah, this was plus. If I copy from here, this was plus. So here I can use the quadratic formula. 3 plus minus 9 minus 4 AC over 2 plus minus 1 over 4. So it's 4 over 4 or 2 over 4. So 1 or half. So I see that I need these values. Three possibilities. Check this value at these points. And if they are not 0, so if I put x is equal to 0 in this equation, I get 2y cubed is 0. So 2y plus 1 minus y cube is 0. And I see that y is equal to 0 is a solution. So I can, if I put that here, I get a 0. But I will have a non-trivial solution from here where y is not equal to 0, and that will make, because all of them have a y over here, this will not be 0 over there. So I can check this by plugging in here for all the y's and then solve for y and check if I have a non-trivial solution where this term does not go to 0. And then from the outside, it seems like we have 3 points. Where tangent is horizontal. Let's do this one. This is called a hyperbola. You have certainly seen these things. And suppose if you want to find formula for tangent to a hyperbola at any point x naught, y naught. So again, you just differentiate 2x over a square minus 2y, y derivative over b square is 0. So 2y, y derivative over b square is 2x over a square. So y derivative is x over y b square over a square. So whatever point you want to compute, you put in that point here, x naught, you will get a y naught from this formula. And this will be your tangent. This will be the slope of the tangent. Where if you want, you can even compute y is plus or minus b square x square minus a square over a. So y naught is plus minus b square x naught square minus a square over a. You plug this in over here. And at any point x naught, you have a formula for the tangent. So I'm gonna stop here. What I'm gonna do is do another tutorial on Thursday and then another one on Friday, because there are lots of different issues, problems, which you probably need some practice with. So I'll do 2 more tutorials before the start of the next week, and I'm gonna post a homework today. And I'll apart from the homework, I'll also suggest some exercises from the book. Well, you can just do all of them from the book and see how you do for the practice. And so homework will be up tonight. Is there any question? Any question?
No, sir.
Okay, let me stop here.